Hey there, math fans. Going to talk about where curves arise. A lot of times students that are studying 3D calculus, they see these parametric curves and they think, where are these coming from? There's two places. If I was going to take, a baseball here and throw it, we could talk about the path that it's following, the motion it follows. What if it hits something, bounces off something? Those are hard problems. Not necessarily for baseball, maybe we can figure out from a parabola, but motion problems involve understanding all the forces involved. So if you want a set of equations that match a realistic situation, it's a challenge. Look at those golfers every day that are on a green, how much effort they put just to hit it a little ways into a hole. Finding a path across a surface is actually a challenge. In math, oftentimes we're trying to study the curve itself, in which case we're not talking about forces or gravity or other things. We're just saying, I would like anything that describes the path I'm interested in. It doesn't necessarily have to be going the right speed or whatever. That frees us up a lot. So this is mostly the perspective in our calculus course is not, we do talk about motion, but we're saying oftentimes we just want to describe something that's on the intersection of two surfaces, which frees us up a lot. Okay, so anyways, here's a few examples of that. And then I'll finish with a practical example of an actual baseball here. This is from a video I made where I was studying the seams of a baseball. So stay tuned and I'll show you that in a second. Okay, first, this is one from my lecture. On the right there, you can see a picture of that first thing. So this is some sort of parabolic cylinder, but turned a little bit. And then the other one is a plane. This is actually a plane. So let's graph that. So the intersection of that is a curve. What if I wanted to study it? So it's kind of the perspective of a large part of what we're doing. We're going to try to parameterize it in some way. Because if I want to know the length of the curve or if I wanted to walk along the curve, these are useful for some things, not useful for others. So I'd like to describe some object moving along it. How do we do that? There's kind of two methods. One is you could randomly pick one of them to be some function of t and then find the others in terms of it, or you can look for circular motion. I don't really see anything where x and y or x and z are both squared, as opposed to this one where I do. And so I'm just going to randomly pick one to be t. Now, if I pick x to be t, I'm going to run into problems right away. Why do I say I'm going to run into problems right away? Well, because I don't know how to solve that for z or y. Well, shoot, that didn't work. And if you go on and take future courses, that course where we use this the most is Math 224. It's the one where you see it the most immediately after this course. And in that course, I have entire review sheets where I talk about, I found this review sheet, how to parameterize from my 224 course. In Math 126, we don't really need to be an expert on parameterizing, but we should have a little bit of a sense of what it's about. Okay, so let's try this being t. That immediately forces our hand. If this is t, then z has to be 2t. The moment you write that, you're actually on forever. If y is t and z is 2d, you're on this plane forever, no matter what else happens. So when I plot this, I already know it's on the plane. So now what? Well, now we know these two things, and we want to know x. And so then I start to solve for x. I say, well, what is x? X is going to be z minus y squared over 2. And since I already know what z and y are, as I said, this gives you lots of freedom. Most math students don't like freedom, but this will work. Sometimes when all three variables are present, it takes more work to combine them. Sometimes it's not even that possible. But here's what I got. So here's this object we're going to watch move along. There it is. I'm going to zoom out a little bit. It's going to, there it comes back in the in screen. Always going too fast. There it is right there. I'm going to decrease these numbers a little bit so we can see it for longer. And it's just going to be in screen here. Go. So that's it. Okay, let's see if it's actually on there. So it's always on this surface because we solved for x to make it happen. We already knew it was always going to be on this surface, so it's on both. You could tweak some of these numbers and it's still going to be on there. That gives us that curve. And now it gives us something to work with. So in future courses, if you wanted to measure it, like what's the length along a certain piece, it's now down to one parameter. We can set up an integral. We can answer a bunch of questions. That's the perspective of Calculus 3 for the most part. We do study motion as well, but like I said, that requires we know a bunch of forces. And often that leads to differential equations, things we don't have. There you go. Okay, so let's look at another one. So that's one parameterization of that. I could have made this something else. I could have made this t cubed, and I would have had to change everything else correspondingly, but it still would have been correct. If there's a circle there, you look to use circular motion in some way. So in this case, I can say x equals cosine of t. Do I have to say t? I could say 2t or 3t. That just depends on how fast I want it to go. So from above, it's going to look like circular motion. That satisfies that. And then you say, hold on, but I need this to be what 5 minus whatever the x is. This comes from an old final I had in Maths 224, where we were measuring something in 3D. I like that one. It's fairly quick to parameterize, and it's interesting. So here's what I have. Sorry, it's drawing more than I want. I have a cylinder. That's the cylinder. Zoom in a little bit. There's that cylinder. Centered at the origin. Here's this plane. I made it too high. There it is. It intersects right there. You can see it's kind of an ellipse on its side. The parameterization I just gave you there, if I plot it and let it go, it looks like this. It's really small. As I look at it, oops, it goes too far. There. If I actually plot the curve, it's this curve. And that's the intersection of those two things. It's on here, and it's always on here. It's that simple. If you tweak the numbers a little bit, like if I make this a 2 or a 3 or something, it's just going to change the speed of it. So for example, if I make it a 3, I'm going to put a 3 in all of those spots, it goes faster. If I make it a 30, it's going to go extremely fast. I have to make all 3 a 30, and it hurts my eyes. Okay. So there are many parameterizations. Some walk faster, some walk slower. All that had to be true is that the equations worked in the surfaces. The points satisfied the equation for the surface. Okay, so let's do one more here where I have a sphere. And then we'll talk about the one that I think is the most interesting. So sphere, plane. So for some reason I want to study. So this would be a step 1. If you wanted to study an intersection of a sphere and a plane, and that may not interest you, but I'm trying to give some situation of how these arise. And I have, well, that's not the one I wanted to show you. That was a different one. Sphere and a plane. And I would like to study that intersection. Well, it looks like some sort of great circle. How would I do it? So in this case, I could solve for t here. I could just have x be t. One correct answer would be x equals t. That forces z to be 2t. And then you would solve for y. And the only y is here, so y would be plus or minus the square root of 1 minus x squared, which would be t squared, minus 2t squared. Now, I didn't actually use that parameterization, but I'll show it to you now. So I'm going to do t square root. I'm going to type this in. I know you can't see what I'm doing. Minus 2t to the second, 2t. Let's see what happens when I type all that in. I actually couldn't put the plus or minus in. The system only allows me to, so it did half of it. That's the one with the plus. So what I have graphed there is this with the plus. There's some disadvantages to this parameterization. Oftentimes in applications you're trying to take derivatives, it's kind of a messy derivative, but it's correct. The other problem is that you have to separate the plus or minus if you do this. So now I'll do it with the minus. Gives me the other side. So there are some practical things about a parameterization. Those are correct parameterizations. If I do the plus and minus, I think I do have a way I can type this in. I get this. That is indeed a correct parameterization. Oftentimes our textbook doesn't allow that, and when you enter it for homework, because it doesn't give you a way to enter plus or minus. And if you only enter one, you're not doing the whole thing. So is there anything else we can do? Sure, let's do one. We can try to reduce the equation down. So let's substitute this in here. We get x squared. And this is just to try to help us. So I'm going to put a 2x into that. Makes it a 4x squared equals 1. And then you have 5x squared plus y squared is 1. And that's actually an ellipse. And we know how to parameterize an ellipse. If you don't know that part. There's two ways to think about this. I often try to just make it look like a circle. In this case, this would have to be the square root of 5x. And so I have the square root of 5x equal cosine and y equals sine. So in other words, x is 1 over the square root of 5. So that's a little maneuver to make it look like circular motion. And now we know what z is. Z is going to be 2 times x. So it's going to be 2 over root 5. So this is the sort of stuff you would do in a future course. How do I parameterize in the nicest way possible? Either for visualizing or for calculation. And usually that's a little easier. And it's that. And it's also nicer to animate because it'll just loop around and it'll do one loop in 2 pi. If I plot the points. Oops, I didn't plot the points. Anyways, that's that curve. Okay, so this leads me to the last thing. Before the beginning of baseball season, I was studying a baseball, and I was thinking about things that might relate to this course, and I saw a study on the seams and how they put a ball together. I knew some of those things, and I read a paper about the shape you get before they put the pieces together. It's 2 little rounded shape. You can watch that video. And then I thought, I think we could approximate that with the intersection of a sphere and a cylinder. And when I did it, I realized actually it didn't make sense, but it made sense if I broke it apart like this. So there's a baseball. I actually used measurements from a baseball. Eventually I hope to print this off. This is before you unroll it or put it together. This is pretty close to accurate. I was surprised how close it was. But I'm actually intersecting with a half cylinder. So how did I draw all of that? I did this. It's because I knew this course. And also in that video, I animated these points along the edge. How did I do that? This way. So that picture you're seeing there of that animation is the intersection of these two things over here. And I'll make this a little higher. So it's the intersection of that fourth example. So I parameterized it. How did I parameterize it? I went, well, we have circular motion here. This might not have been the best way. I didn't think about it too hard. I just wanted to make it work. So I said, I want x minus 0.235 equal to 1.063 cosine of t. And I should note, this is this radius, so I needed this to come out, and then I had z be 1.063 sine of t. That made sure it was on the cylinder. And then I need to know what y was. But I knew what x was, and I knew what z was. I could have thought harder, but I just solved for y. Y is the square root of everything else, so it's the square root of 1.45 squared. minus x squared. So I took whatever x was and squared it, minus whatever z was squared it. And that's how I typed it in. I moved this to the other side, and I typed all that in. So I said plus 0.235. That was x. And I just copied and pasted. Let me make this a little smaller so you can see it. I copied and pasted that in to these places. So it's actually not that bad to animate some of these things. A lot of the animation I do. And then I had to adjust the parameters, what I was going to allow t to be, so that I could see just that. And then I plotted the plus and minus, the one below and the one above. And then I did the same thing on the other side here. And I plotted a point moving on the other side. Now, I really wanted it to just be one object that moves all the way around, but since my equations were kind of changing, I just did that to get a picture of what the seams are. So there's me parameterizing a bug moving along the curve of the seams of a baseball. And then I used those to figure out how long the seams of the baseball were, and I compared that with actual values. So I thought that'd be interesting just to see an application of something. That's part of why I'm making these sorts of things. It's not hard to find applications, and I hope that just makes it more interesting. All right, thanks for watching.